Hello everyone, this video is about common base amplifier. Common base amplifier is the bipolar junctions amplifier with the base terminal shorted to AC ground, AC or DC ground, okay? So the circuit for the common base amplifier would most likely similar to this one. We C, and then RC, and then you have a transistor here. And then you can ground this terminal directly, depending on the requirement. Or you can do this through a capacitor. And then the input is to be tapped from here. So to analyze the circuits, again, you can use the most common methodology. First, replace the transistor with a small signal diagram. And let's do this with pi model. And amplify, and then we have a current source, a dependent current source in pi. And let's assume the transistor is not perfect. It has a finite R0 represents the resistance due to the early event. So the equivalent circuit will be like this. You have an R0 and output. The transistor, and the input is to be tapped from the E terminal. So it will be V in, and the output and the base terminal is to be shorted to ground. And the output will be tapped in here. So we have an output here, and the output will be short, will be connected to RC, which is in turn connected to the ground, the AC ground. So we have the equivalent circuit for this common base emitter, common base amplifier. The next thing is to analyze the circuit. V pi in here represents the voltage V pi here. And based on my direct observation, V pi is actually equals to negative E in. So V pi is equals to negative E in. The base current will remain low. Will remain insignificant as compared to the emitter current. So the first assumption here is IE or IC is substantially larger than the base current, which is true. So if it is the case, we can just temporarily forget about the base circuit because literally the circuit forms from the circuits connected to the base terminal is literally open circuit. So we can for the time being ignore this part. So we have only this part here, and based on this part, we are going to work out uh, the transfer functions. Now, the first thing that we can do based on these circuits is to use uh, Teflon to Norton analysis to convert these parallel combinations into a series connection between analog and the dependent current source. So the first step that I use is here. And we have a voltage source with the plus in this side and minus in the right side. The voltage source here is Gm V V pi, and then analog, and then we have an analog here. And again, we can simply say V out, which is connected to RC here. So the circuit here is further simplified into this one. And we temporarily ignore the network connected to the base. So apply Kirchhoff's voltage law. The voltage Vout, which is this one, is equal to the potential difference across the resistor here. And we have Vout here, Vin here. So we can say that Vout, always have this mistake. Vout is equals to this voltage plus, actually minus, because the plus sign is here. And R naught. And the voltage here is going to be V in. So now we are now trying to get the transfer functions from this equation. And before doing this, we need to remove all the variables, convert them into an expression involving V out and V in. Now, the first thing that we need to know is V pi is equivalent to minus V in. So we can just simplify the equation on the fly. Minus R plus and R log V in. Now, IC, what is IC? Based on this equation, based on the law here, IC is equals to minus V naught divided by RC. Okay, so now we just directly substitute this variable, this expression into IC here. So we have V naught and then R naught and then RC. So we are almost there now. First we have this expression. By the way, there's a minus here. Okay, so there is a minus here. So the next thing that we are going to do is to do some algebraic manipulation. Now this one we log and then 1 plus R divided by RC. So this is going to be the left side of the equation. The right side involves these two terms. And we can do that. 1 plus R no, and then GM. Now, before going forward, before going to the next step, let's just guess, just work out the value of R times GM. R is equals to VA divided by IC. GM is equals to IC divided by VT. So the product of these two variables is going to be IC divided by VT times VA divided by IC. So these two terms cancel out. We end up with VA divided by VT. And VA is normally a large value. VT is the thermal voltage. The value for room temperature, the value is normally given as 0.026. So the end result is this value is going to be huge, much larger than 1. So based on this analysis, it is logical to approximate this equation into here, and then 1 is redundant. And the left side of the equation is going to be 1 plus R log and RC. Now, the voltage gain, according to here, is V out divided by V in. V out, V in is going to be GM R log, and then plus 1 plus R log and RC. And if we multiply the top and bottom with RC, we get this expression. GM R log and then RC. And the bottom one is RC plus R log. And if you take a look here, this one together with, I'm talking about this expression. This one is actually R log in parallel with RC. So finally, we are going to further simplify uh, the expression, and by my observation, the voltage gain is going to be R in parallel with RC. Okay, you can read it. Okay, so this is the voltage gain, and I'm going to highlight this. The next thing is to work out what the current gain. The output current is based on this diagram is minus IC. Okay, this is I no. So current gain I know is going to be minus IC, and the input current here is this one. It is minus IE. Minus IE, and minus IC is minus beta times IB, and minus IE is equals to 1 plus beta times IB. So the ratio, the current gain, which is like this, right, is I log the IL divided by 1 IE. And if my observation is correct, it is equals to beta IB and then plus beta IB and minus, and then the final expression is here. Okay, so it's almost 1. There will not be any extraordinary current gain in the common base amplifier, but the voltage gain is high. The voltage gain depends on GM and also RC. If we have very large value of RC, then if you have chosen a good quality NPN transistor, then the voltage gain will be naturally high. Now, we have already discovered this thing, and what about the input resistance and the output resistance? So now we are going to use this way to explain to you the input resistance, and we are going to retain this expression. Let me see. Okay. input resistance by definition is R in, V in divided by the input current. The input current in this case is minus IE. And what is IE? The question is. And IE is equals to V in, and then is equals to minus I and 1 plus beta divided by beta, and then IC. And the question now is, what is IC? Then we can just use the expression here to work it out. V out, and then and IC according to here is V naught divided by RC and minus, right? Do not forget the minus sign. So minus and minus become plus. So we don't need this. Now we can do this RC and 1 plus beta, and what we can do is to make use of what we have done before. And RC 1 plus beta divided by beta, and this one C and R naught. So this is the input impedance. And because one or equally, right? We can do that instead of reaching space. Now beta divided by 1 over beta is almost 1. So we can approximate this expression. And RC and this expression are in parallel with RC. What happens if R is very large, close to infinity? So if R is large, then we can say that the whole expression is almost equal to 1 over Gm. Yeah, this one is 1 and this one is 1. So the final expression, the final approximate formula is 1 over Gm, as long as the early effect is log large. So I can say if R is huge. Now the input impedance has been found, the input resistance. And what about the output resistance? What my suggestion is we just drop this input voltage, and then we find out from there. So based on what I have done, let's withdraw the circuits first. The circuit with the input shorted. So let's say yeah, we are running over. Yeah, let's do it here. So this one is output resistance. And let's withdraw the circuit. And you have a R pi, which is connected to the ground. And you have CM R E pi and R and here is IC and VO, and you have a RC, and this one is different from this one here. We in. So what I suggest is we sort this voltage source. This is the way how we extract the output impedance. Sort this, V in becomes 0. And with this in mind, because V pi is equals to minus V in, this one is also going to be 0. So there, this one is meaningless. So in this case, we measure the output resistance here based on what we have analyzed here. The output resistance by looking into here is going to be the parallel of RC and R. So the output impedance can be high. The voltage gain is definitely high. There is no current gain because the current gain is almost 1. The input resistance is unfortunately very low, 1 divided by GM. This is probably large number. So that's all. So we have this one, yeah, the voltage gain and the output resistance, and we also have the input resistance, and we have also divide the current gain. If you have any questions, please leave your questions to the comments box of the video, and if we have time, we will address your questions. And thank you very much for attending the lectures here. Bye-bye.